Okay, so thermosetting plastics, unit 5, part 3. The one that can go on heat cycle. Thermosetting plastics and thermoplastic, then we're gonna take a look at again the structural difference. So when you take a look at the thermosetting plastic, you already know it can go through only one heat cycle, yeah? And you cannot reprocess, we know that. So thermosetting plastics are synthetic polymers. So when you go into the molecular structure, you're gonna see cross links, right? Between these chains, you will see the cross links. And that's the difference, major difference between thermosetting and thermoplastic. For thermoplastic, you remember the 3 configuration, yeah? Linear, and then your branch, and then your network. But thermosetting, you've got cross links, yeah? So what's up with the cross links? The cross links, they create strong bonds. And these bonds is going to prevent the plastic from being reprocessed, okay, once they are cured. Cure means setting into a shape you can reprocess. So therefore they cannot be recycled or reprocessed, okay? Therefore you have to sort it out away from the thermoplastic that can be recycled. Okay, so let's get into this structured diagram. So here is the molecular structure, and you can see how neatly they are cross-linked, see? Over there in thermoplastics, even though they are in network, they are not all like, organized network. They're just whatever network. That's why we call it network. Here we call it cross-link because they are, okay, systematically cross-linked like that. Therefore, give you higher strength, yeah? So we're going to take a look at the history. Industrial technology, we're not heavy on history. This is not a history major class. So it just touch up, it's going to start from 1800. So that's the first development of plastic. They've been trying since that time, but then became successful in the middle of 19th century because we started to do commercial plastic by replacing the ivory for billiard boards because ivory is so expensive. Because this one comes from the some animals like elephants, yeah. So billiard balls are now made of plastic, commercially synthesized of plastics. Phenolate, urea, formaldehyde. Okay, plastics are very first type of plastics, and they came out early 20th century. So this is a guy named Leo Bexlin, alright, that's in 1909. So what he did is he started the Bakelite Plastics Company, okay, and they're all thermosets, by the way, and we call them thermosetting plastic. So the word setting means like it won't return back to the original form, okay, it can go through one heat cycle, and then you will set the plastic, and plastic will gonna stay right out there at that shape, yeah. Okay, so now we will classify. We have phenolics, urethanes, silicones, urea, and epoxy, your melamine plates, we call them monoresins, and unsaturated polyesters. So they're all thermosetting plastics. Thermosetting, we're going to form not only just a regular polymerization, we're going to do condensation or polymerization. So it's a little different from thermoplastics. So the process of chemical reaction, condensation or polymerization, because there is chemical reaction in this process. So what is that chemical reaction? We're going to break the molecular bond with heat, pressure, and then catalyst. Okay? Catalyst is just an agent to make the reaction go faster. So the reaction between monomer is chemical, and so you're going to get water as a byproduct. So where is the reaction happening? The reaction is happening between the monomers inside of that polymer, yeah? So we are making polymer by reacting the monomers in a chemical way, yeah? Not just adding. In thermoplastics, polymerization is adding one molecule to another physically. Here is we're adding the monomer by reacting them chemically. Yeah. And what is a chemical reaction? We're taking the water out of it. Yes, and we call that condensation. Polyethylene glycol terephthalate. So when you look at it, this is just an example. Okay, and this polymer it's gonna go through condensation or polymerization. Okay, and we're gonna produce a long chain of dacron. Dacron is other people call it dacron. It doesn't really matter. Okay, and this is the molecular name, right? The whole thing, really complex molecule right in there. So how do we do the chemical reaction? We're going to take the water out. Yeah. So when you look at it, this is a monomer. So the monomer has water. Okay. And we're going to take that water out. So here is your OH, the very first one, and there's a OH from the other monomer. Yeah. And you're going to take this out. You're going to take that out, and they're going to react to each other and form a dacron. Okay. So we heat, pressure, and catalyst, and this little guy is a catalyst. So what is it trying to do? Trying to get the water out of it. So this monomer is gonna bond together, yeah? And the catalyst that we use here is ethylene glycol, right here, ethylene glycol. And this is your first monomer, and that is your second monomer. And the monomers are called terephthalic acid, okay? And we're gonna put alcohol, this is your glycol, into the acid, and the acid are going to form monomer. Each monomer is going to form the polymers, okay? And we're extracting the water out of it. And you won't be able to see it, so I recommend you to write the equation down if you can. Yes, you don't have to even write the whole thing. You can write like this, okay? Here is just a terephthalic, okay, and then it has a OH right here, you know, OH right here, and you have another terephthalic on this side, okay, and you have another OH right there, okay, and we're gonna spike ethylene glycol, this guy right there, okay, and that's your ethylene glycol. This is CH2 and then CH2, and then you have a 2 OH right there, okay. So you can just do like this, okay? And then you can put right there on this side. We will take only H because water is H2O, so you're gonna need only H out of it, yeah? So now this guy is gonna help to remove that OH, and then this guy is gonna help remove this OH, so this 2 is gonna cross-link, yeah? So that's what's happening. So that's the way you gotta study, by drawing diagram. Yes, so the STEM major S, we're in science, engineering, technology, and mathematics, and you have to learn how to draw diagrams, okay? Drawing a diagram is a lot easier also to retain the knowledge that you just read or watch or, listen. It can stay in your brain longer if you draw diagrams, yeah? Okay, so polymer chain production. So we go back to thermoplastic, right? Part 1 and 2, they are produced by using additive polymerization. Like I say, we add the monomer, right, to each other and we link them physically into either linear chain or branches chain or the network chain, right? Here is different, right? Here is we're doing the condensation or polymerization. So when you take a look at the carbon carefully, you will see two little bars right there. That's mean it has a double bond right there. They're staying together with a double bond, meaning like there are 4 electrons right in there. Yeah. So we're gonna break one bond by using heat, pressure, or catalysts. So when you break a bond has 2 electrons right in there. So one electron is gonna Alright, let's stick with this carbon, and another electron is going to stick with that carbon with their attractive forces, right? So you can see a little electron floating around that carbon, hanging around with other stuff. Your H, is still there. So we call that free radical. So as soon as the electron is free, it has a tendency to grab something around in the neighborhood, okay? So the single covalent bond, after the bond, double bond has broken, has at least a one unpaired electron. It wants to pair up with something, So they're looking for the next molecule around, okay, all around that little carbon with a free radical to bond. And as soon as it finds another molecule, it's going to form, right? React it. So they form a polymer chain that way, right? We use heat pressure catalysts, break the double bond, make the single bond, and float a electron for each, because there are two electrons in one single bond. So each one of the electrons is going to stay around each carbon, and these free radicals are going to look for another molecule, alright, and then they chain them up, So that's what's happening, condensation or polymerization. So mechanical and physical properties. Thermosetting plastic and thermoplastics, they have different structures, so they have different properties. Thermosets, higher surface temperature, they have higher tensile strength, they have higher compressive strength, and they're stiff, okay, generally stiffer. And these are what thermosetting plastic will look like. Here is a table, and we have various properties of selected thermosets, okay, these are plastic family, and thermoplastics. So we have this one, thermoplastics, thermosets, and then this one is your thermoplastics, okay? So epoxy, phenolic, melamines, urethanes, or thermosets. They should write thermoset that way. And thermoplastics are this one, high density, HDP, LDPH, and then you have polystyrene, polypropylene, and your ABS. And here we can take a look at their tensile strength. See how the numbers, just pay attention. We usually just look at the zero, right? So when you see 3 zeros, and here is 3 0, but still have numbers, and this won't go up. Then you can see like this is higher here. Modulus of elasticity, it's like 10 to the power 6 psi. Okay. Don't forget there's also another unit here. Now we have differences right there, see? Relatively. Your impact, resistance, your compression, and then your service temperature, okay? They're basically higher, and it's also higher. Impact, relatively higher, but this one kind of, okay, about the same for polystyrene and melamines. Okay, then the first group, phenolics. Phenolics, the real term is a phenol, formaldehyde. It's the oldest plastic and very cheap. And we have different grades for phenolics. We have general phenolics, impact resistant ones, electrical ones, heat resistant ones, special, and non-bleeding. They have high stiffness, high impact resistance. They are readily moldable, so we can mold it into containers like that. They have high relative strength, and they're good insulators. So what are we using? This is just don't limit yourself to here, okay? But there are many other products. We're just giving a few of them here. So various non-astrals, keys, right? Keys, housing like that. Not the key, the metal part, okay? The plastic part. And the radio and TV cabinets, and the auto ignition parts. So this is a phenolic preform on the left, okay? And we're going to compress in the die. Die is just a cavity, so that's just a mold to make the part on the right. Preforms, they have like approximate shape as a die cavity. Alright, next group, urethane plastics, chemical term polyurethanes. So these are the plastic based on polyesters. We also call them polyether resin, okay, and some people just call resin. They have special characters. They have excellent tensile strength, elasticity, excellent. They have good, alright, ozone resistant, good abrasion resistant. They're resistant to chemicals and oils. They're resistant to certain fuels. So we use them in solid tire for big trucks, semi, yeah? The roller, shock impact devices, auto bumpers, foam for refrigerator insulation, foam for padded areas, foam for cavity fillings for boats, foam for furniture cushions, foam for sponges, yeah? So there are many different parts. So some people who hate plastic and say, that's because they're concentrating. They have very narrow mind and they concentrate only in storage or bags or supermarket bags, right? Because they don't want to clean up. Usually housewives shouting, women, old women shouting. So anyways, they don't really know how much our world is using plastics. But then some of the applications are a necessity, right? Many various products. Even if they want to go all paper or just pure metal, that can't happen in real life. Just can't. And sometimes they don't know even the materials they're using are plastics at all. Okay, so in their mind, it's just seeing in the supermarket some plastic bags and messing around in the kitchen, and they want to shout. I gotta tell my mother all the time about that. No, okay, mom, plastic is actually, we're living in the age of plastics. Okay, not age of bronze, not age of iron, not age of copper. Totally plastic, and we will continue because it's very convenient and it's easy to process, and you can. The most important thing is you can synthesize, alright? Meaning like you can depend on the nature, okay? But again, it takes time, right, to master the how to incinerate. It's coming out, it's just like too expensive that not all the company can be able to perfectly dispose in the right way. But the method is already there. We just have to make it cheap, okay? So anyway, so don't hate plastic because we heavily use in many industries. Okay, you can't live without it. From medicines into food, okay, and your appliances, and even I believe in the future we will be using it in making construction. Okay, even though already penetrating a lot of the parts made in very strong tensile strength. Okay, really high plastic that acts as metal. We already see the nylon fiber, right? Glass fiber, nylon. It's so important because you can also use that in construction, right? And it's a great help to the space, right? We're getting into the space era as well, so everybody want to go into the space and explore. We have already explored the land, right, and the sea, the continents, the air. Now we're going to get into space to explore more to see what's out there, So plastic also is really good, right, for those kind of purposes. You can't just hate by narrowing your mind. You've got to know everything that's going on in the world, yeah? Okay, anyway, let's go on silicone. So that's another group in thermosetting plastics. So inorganic plastics and the monomers, what we're going to do is, okay, the monomers, they have oxygen atoms, right? So when you look at the monomer, you can see the little oxygen atoms right there, see 3, attached to the silicone, right? This little guy, silicone atoms. And we call that inorganic. There's a silicone in it and oxygen in it, okay? More than organics are your C, mostly C and H, okay, and O. So I have one inorganic silicone right in there. That's why we call it silicone. So silicon is spiked into the organic material, so inorganic plastic. So these monomers are bonded together, right, with silicon, oxygen, and silicon. So silicon, oxygen, silicon, cross-linking. Yeah. Again, cross-links are the chemical reaction. So therefore, you can see the chemical reaction between the silicon, oxygen, and silicon. But then they are expensive, right? They're very expensive. So we use them in aircraft and aerospace. So you can see these. So all these things making it pretty. You like it because it looks shining and right, looks new. So high performance product. We make them in the sealant, gasket, electronic industry like that. Okay. So they have low moisture absorption. That's why we use in aircraft. Resistant to petroleum products, resistant to acids, and high heat resistance. Okay. So pretty good qualities they've got. Epoxies. So if you think about epoxy, always remember your auto epoxies, metal, when you want to glue them. So they're commonly known as adhesives, but then they're a little more costly than the other plastics. They have great properties like excellent mechanical properties, electrical, heat resistant, hard, reasonable tensile strength, adhesion. They can glue metal, right? They can also glue non-metal, and they also have dielectric strength. So we use them chemical resistant coating. We use them the encapsulator like that for electronic components. Okay. Melamines. So if you think about melamines, we remember the kitchen, your mother's plates. Especially they use it for small kids because they don't want to break the plates. So aminoplastic family melamines, or you call it urea as well. So they represent amino resin. This is just plastic raw material. Melamine or urea, you're going to add spike formaldehyde, and you're going to get amino resin. We use it to make products. Hardest plastic, but they have poor impact strength. So we use it for electrical switch plates like that. At home, you can see, A long time ago they used metal. Now we're replacing everything with plastic. Wiring devices, housing for small appliances, button dishes, and then tableware, tabletops. Instead of marble, you can use melamines, countertops, adhesive, and laminated wood products. The next group is your unsaturated polyesters. So when you look at the production, they're just a synthetic resins. You're going to produce it by condensation of acids. And so what do? We use the allyl alcohol or ethylene glycol in condensation of acid. Again, we're going to go light on the chemical because we're not in the chemical engineering technology. Okay, we're on the industrial technology that you have to deal with machines, right? Making or management kind or business. So when polymerize, cross-linking is going to happen because the chemical reaction is happening. So something is going to link to something, and then they're going to polymerize. So you got a long molecular chain, right, coming out from the chemical reaction. So when you take a look at the property, they have high strength, high adhesion, they have good chemical resistance. So we use them in binder for glass fiber reinforced plastic products. We use them in glass reinforced plastic, so that's about 75% of polyester production we use it. In the United States, of course. And then textile fibers and sheet, film stock, costume, film stocks are like that for the entertainment industry. Costume resins, right? Resins to cost more product. We make buttons, electrical components, and then we use the architectural shapes. Alright, that's it for part 3. Again, I'm try to study slowly, because it's really confusing. They all look the same. But you'll get it over time,